Welcome to the deep dive. Today we're digging into something fundamental. Why aren't real-world materials, the metal in your phone or your car, as super strong as scientists first thought perfect crystals should be? It's a fantastic question, and it takes us right down to the atomic level. So our deep dive today is focused on a key chapter from Callister and Rathwish's Materials, Science, and Engineering. We're talking dislocations and strengthening mechanisms. We'll break it down so you can really get it, even without the textbook diagrams right in front of you.
Oh,
Especially helpful if you're maybe tackling this in a college course right now.
absolutely. And this isn't just academic theory. Understanding these tiny defects, these dislocations, is crucial for engineers. It lets us design materials with specific properties. Think about the strength needed for an aluminum can versus a jet engine turbine blade. It's all about controlling these microscopic mechanisms.
Right. So our mission is to unpack how materials deform permanently and how engineers cleverly manipulate things at this tiny scale to make materials tougher or stronger or maybe more workable. Okay, let's start with the basics. Deformation. We've talked before about elastic deformation, like stretching a rubber band, it snaps back. But here, we're zeroing in on plastic deformation. That's the permanent kind, like bending a metal spoon. It stays bent.
Exactly. Strength and hardness, fundamentally, they're just measures of how much a material resists that permanent shape change. And microscopically, plastic deformation isn't just smooth stretching. It's actually the coordinated movement of, well, billions upon billions of atoms. Bonds break, bonds reform. In crystalline materials, like metals, the main actors in this atomic dance are dislocations, these linear, line-like defects in the crystal structure.
And this is where that initial puzzle comes in, right? The huge gap between the predicted strength of a perfect crystal and what was actually measured.
Precisely. Early calculations suggested perfect crystals should be incredibly strong, far stronger than anything observed. That discrepancy was huge. It led scientists back in the 1930s to theorize the existence of these linear defects dislocations. They couldn't see them directly then, not until the electron microscope came along in the 50s. But since then, dislocation theory has just been fundamental. It explains so much about how materials behave mechanically.
Okay, so let's get a clearer picture of these dislocations. What are the main types we need to know about?
There are really two fundamental types: the edge dislocation and the screw dislocation. In reality, most dislocations are actually a mix of the two, what we call mixed dislocations. But let's start with the edge type. Imagine a perfect grid of atoms, like a perfectly stacked set of Lego bricks. Now, picture inserting an extra half plane of atoms partway into that stack, from the top down. It stops somewhere inside the crystal. The edge dislocation is the line that runs along the bottom edge of that incomplete plane. It's the boundary of that extra half sheet.
Okay, I can sort of picture that, like a fault line where that extra layer ends. What about the screw type? You said that one's harder.
Yeah, screw dislocations are a bit more abstract. Think less about an extra plane and more about a twisting or shearing action. Imagine you cut partway into a crystal block, and then you shift one side relative to the other, parallel to the cut face. This creates a sort of spiral ramp structure winding around the dislocation line. The line itself runs down the center of this atomic spiral staircase, if you will.
Spiral ramp. Okay, so we have these edge and screw types. How do they actually move to cause that permanent deformation we talked about?
Right. Plastic deformation is basically the result of huge numbers of these dislocations moving. Let's take the edge dislocation first. It's maybe easier to visualize. When you apply a shear stress, sort of a sideways push, that extra half plane gets nudged. It essentially hops one atomic spacing over, bonds in front of it break, and new bonds form behind it. This ripple effect propagates the dislocation line through the crystal.
So the defect itself moves, and that movement is what causes the overall shape change.
Exactly. Before the dislocation arrives and after it leaves, the crystal lattice is perfect again in that local region. The disruption is just temporary as it passes through, but the net result, after it moves all the way across, might be a tiny step, just one atom high on the crystal surface.
That sounds incredibly efficient in a way, almost like
Like a caterpillar. That's the classic analogy. Think about how a caterpillar moves. It bunches up a section, creates a hump, and that hump travels down its body. The hump is like our extra half plane of atoms. The movement of that localized hump moves the whole caterpillar forward. Same idea with the dislocation moving through the crystal.
Okay, the caterpillar analogy helps. And screw dislocations. Do they move like caterpillars too?
They also move under shear stress, but here's a key difference. A screw dislocation moves perpendicular to the direction of the applied shear stress. An edge dislocation moves parallel to it. It's a different geometry of movement, but the end result, the overall plastic deformation, is the same for both types.
How common are these? Are we talking like one or two per crystal or?
Yeah. Oh, far more than that. Pretty much all crystalline materials, especially metals, are riddled with dislocations. They get introduced during solidification or when the material is bent or stressed, or even from temperature changes. We measure them using dislocation density, the total length of dislocation lines in a cubic millimeter, say. In a very carefully grown, near perfect crystal, it might be low, maybe 1,000 millimeters per cubic millimeter, but in a heavily deformed metal, like one that's been hammered or rolled, it can shoot up to 10 billion millimeters per cubic millimeter, or even higher. Huge numbers.
Wow, 10 billion. Okay. And you mentioned they interact. They don't just move independently.
Right, they definitely interact. And this is crucial for strengthening. They interact because each dislocation creates a little zone of distortion, a strain field, in the lattice around it.
Strain field.
Yeah,
Like stretched or compressed atoms nearby.
exactly. Around an edge dislocation, the atoms just above that extra half plane are squeezed together. That's compressive strain. Below it, atoms are pulled apart tensile strain. Screw dislocations create primarily shear strains. These strain fields radiate outwards, kind of like ripples.
So these ripples, these strain fields, can push or pull on other nearby dislocations.
Precisely. If you have two edge dislocations of the same sign, say, both have the extra half plane on top on the same glide plane, their compressive fields will repel each other. They push apart. But if they have opposite signs, one extra plane above, one below on the same plane, their strain fields, compressive meets tensile, will attract each other. And if they meet, they can actually annihilate each other, canceling out the defects and leaving behind a region of perfect crystal lattice.
Wait, if they can annihilate, how does the density skyrocket during deformation, like you said? Shouldn't it decrease?
Ugh, good question. It's because deformation doesn't just move existing dislocations, it also creates vast numbers of new ones. Existing dislocations can act as sources, spawning more dislocations. Plus, things like grain boundaries, tiny internal flaws, even surface scratches can act as nucleation sites where new dislocations form under stress. So multiplication vastly outpaces annihilation during plastic deformation.
Okay, so multiplication is key. Now, you mentioned dislocations move on a glide plane. Do they just pick any old plane?
No, not at all. There's a strong preference. Dislocation motion is easiest along specific crystallographic planes and in specific crystallographic directions within those planes. This preferred plane and direction combination is called a slip system.
And what makes a plane or direction preferred?
It comes down to atomic packing. The slip plane is almost always the plane with the highest density of atoms, the most tightly packed plane, and the slip direction within that plane is the direction where atoms are packed most closely together, the highest linear density. Think of it like sliding layers of marbles. They slide most easily along the densest packed layers and directions. It requires the least amount of atomic shuffling or distortion.
Can you give us an example? Say for a common metal structure like copper or aluminum.
Sure. Copper and aluminum have a face-centered cubic, or FCC, structure. In FCC, the most densely packed planes are a family called the planes. Within any one of those planes, the directions of closest packing are the 110 type directions. So the slip system for FCC metals is designated 110, and importantly, there isn't just one such plane or direction. In FCC, there are 4 distinct type planes, and within each of those, 3 independent 110 directions. That gives a total of 4 times 3, or 12, independent slip systems.
12 ways for dislocations to move easily. And does the number of slip systems matter for the material's overall behavior?
Hugely important. Metals with a large number of slip systems, like FCC metals, copper, aluminum, gold, and also body-centered cubic, BCC, metals, like iron at room temp, tend to be very ductile. Ductile means they can undergo a lot of plastic deformation before fracturing. Why? Because dislocations have many available paths to move along. Conversely, metals with fewer active sleep systems, like many hexagonal close-packed or HCP metals, zinc, magnesium, titanium at room temp, are often more brittle. Dislocation motion is restricted, so they fracture more easily instead of deforming.
That makes sense. More pathways means more ability to deform. Now, how do we know when slip actually starts in, say, a single crystal?
For slip to begin, it's not just about the overall stress you apply, it's about the shear stress component acting specifically along that slip plane and in that slip direction. We call this the resolved shear stress. Even if you just pull on a crystal, tensile stress, there will be shear components on planes oriented at an angle to the pull direction. Slip initiates when the resolved shear stress on the most favorably oriented slip system reaches a certain threshold value. This threshold is called the critical resolved shear stress, often abbreviated TOWRS, tau CRSS. It's a fundamental property of the material representing the minimum shear needed to get dislocations moving.
And what does that look like if you deform a single crystal? Can you see it?
You can. If you take a polished single crystal and gently deform it, you'll start to see faint lines appearing on the surface. As deformation continues, these become distinct steps. These steps, which often run parallel to each other around the crystal, are called slip lines. Each line or step is the visible evidence of thousands or millions of dislocations having exited the crystal along the same slip plane.
Fascinating. Okay, but most materials we use aren't single crystals, right? They're made of many tiny grains. Polycrystalline materials. How does deformation work there?
Right, that's the much more common scenario. And deformation in polycrystalline materials is inherently more complex.
Why the extra complexity?
Because all those individual tiny crystals or grains are oriented randomly relative to each other. When you apply a stress, slip will start in each grain, but on whichever of its slip systems happens to be best aligned with the stress. So if you looked under a microscope at a deformed piece of polycrystalline copper, you'd see slip lines within each grain, but the lines in one grain would likely be oriented differently from the lines in its neighbors.
And how do the grains themselves change shape during this?
The individual grains distort to accommodate the overall deformation, but they have to maintain continuity at the grain boundaries where they meet their neighbors. Grains that might start out roughly spherical or equiaxed tend to get elongated in the direction of the applied stress. Think about rolling out dough. The initially roundish clumps get flattened and stretched. Same idea with metal grains during rolling or drawing.
You mentioned earlier that this structure actually makes polycrystalline metals stronger than single crystals of the same material. Why is that?
It mainly comes down to the grain boundaries acting as barriers. Even if one grain is perfectly oriented for easy slip, its neighbors probably aren't. Those neighbors effectively constrain the first grain, preventing it from deforming easily. To get the whole material to yield, you need to apply a higher overall stress to overcome the resistance of all those less favorably oriented grains and push dislocations across or around those boundaries.
So the boundaries are like internal roadblocks for dislocations.
Yeah.
Now, is slip the only way metals can deform plastically?
Not quite. There's another mechanism called twinning. It's particularly relevant for some BCC and HCP metals, especially under certain conditions like low temperatures or very rapid loading. A twin is a region within a crystal where the atomic arrangement formed a mirror image of the arrangement in the rest of the crystal across a specific plane called the twin boundary.
How is that different from slip? It sounds like just another way atoms move.
The key difference is the crystallographic orientation. With slip, the lattice orientation is the same above and below the slip plane. Atoms just shift by whole atomic distances. With twinning, there's a distinct reorientation of the lattice across the twin boundary. Also, the atomic displacements involved in forming a twin are usually less than a full interatomic spacing.
Does twinning contribute a lot to the overall deformation?
Usually, the direct amount of plastic strain from twinning itself is small compared to slip, but its importance is more subtle. The real significance of twinning is that the reorientation it causes within the twinned region might place existing slip systems into an orientation that is now much more favorable for slip to occur under the applied stress. So twinning can sort of unlock slip in situations where it might otherwise be difficult, acting as a complementary deformation mechanism.
Okay, this is great. We've explored dislocations, how they move via slip, the role of slip systems, grain boundaries, and even twinning. Now let's tie it all together. How do engineers use this knowledge to make materials stronger?
The central principle is beautifully simple, really, since macroscopic plastic deformation requires the movement of countless dislocations.
If you make it harder for dislocations to move, you make the material stronger.
Precisely. Anything that hinders or restricts dislocation motion will increase the material's resistance to plastic deformation, meaning it becomes harder and stronger. Virtually every method used to strengthen metals relies on this fundamental idea: impede dislocation mobility.
And today we're focusing on three main ways to do that in single-phase metals.
Yes, the three workhorses are strengthening by grain size reduction, solid solution strengthening, and strain hardening, also known as cold working.
Let's take them one by one. First, grain size reduction. How does making the grain smaller make the metal stronger?
As we touched on, grain boundaries are excellent barriers to dislocation motion. Remember, a dislocation moving in one grain typically has to change its direction to move into the next grain because the crystal lattices are oriented differently. Also, the atomic disorder at the boundary itself disrupts the continuity of the slip planes, so dislocations tend to get held up or pile up at grain boundaries. While these pileups can eventually generate enough stress to start dislocations moving in the next grain, it requires a significantly higher applied stress compared to moving through a single grain.
So if you have more boundaries,
If you have smaller grains, you have a much larger total area of grain boundaries within the same volume of material. More boundaries mean more obstacles, more impediment to dislocation motion. Therefore, a fine-grained material is consistently harder and stronger than a coarse-grained version of the same material. This is famously described by the Hall-Petch equation, which shows yield strength increasing as the grain size decreases.
and does grain size affect other properties too?
Yes, importantly, reducing grain size not only increases strength, but often also improves the material's toughness, its resistance to fracture. It's one of the few methods that can improve both strength and toughness simultaneously.
Okay, strategy one, make grains smaller. What's the second method? Solid solution strengthening.
Right. This involves intentionally adding impurity atoms of a different element into the host metal's crystal lattice. Think of making an alloy, like adding nickel to copper to make brass, or carbon to iron to make steel. High purity metals are almost always softer and weaker than alloys made from them. Adding these solute atoms increases strength and hardness.
But how does adding just a few different atoms stop dislocations?
Those impurity atoms, whether they substitute for a host atom or squeeze into the gaps, interstitial, don't fit perfectly. They distort the lattice locally, creating their own little strain fields. A smaller impurity atom might pull surrounding host atoms inward, creating a local tensile strain. A larger one pushes them outward, causing compressive strain. Now, these impurity atoms tend to migrate towards dislocations because their strain fields can partially cancel out the dislocation's own strain field. For example, a small impurity atom, tensile field, might move near the compressed region above an edge dislocation line. This interaction lowers the overall energy of the system, making it energetically favorable for the impurity atom to sit near the dislocation core.
Ah, so the impurities sort of cluster around the dislocations and anchor them.
Exactly. They effectively pin the dislocations. To move the dislocation away from these pinning points requires extra force, a higher applied stress. This increased resistance to dislocation motion translates directly into increased strength and hardness for the alloy. It's a very common and effective strengthening method.
Makes sense. Okay, third method, strain hardening. This is the one you mentioned is also called cold working.
Yes, strain hardening, work hardening, cold working, they all refer to the same phenomenon. A ductile metal becoming harder and stronger as it is plastically deformed at a relatively low temperature, below its recrystallization temperature, which we'll get to.
Like bending a wire back and forth, it gets harder to bend each time.
That's the classic example. We quantify the amount of deformation using percent cold work, CW, which usually relates to how much the cross-sectional area has been reduced, and the effect is quite dramatic. As you increase the CW, the metal's yield strength and tensile strength go up significantly. You can see this clearly on stress-strain curves.
But there's usually a trade-off, right?
Always a trade-off. As strength increases with cold work, the ductility, the ability to deform further without fracturing, decreases. The material becomes more brittle.
What's happening inside the metal to cause this hardening effect?
It comes back to those dislocation interactions. Remember how deformation creates more dislocation?
Right, the density skyrockets.
Exactly. So as you deform the metal, the dislocation density increases enormously. The average distance between dislocations gets smaller and smaller. All these dislocations have their own strain fields, and these fields start to interact and impede each other's motion. It becomes a dislocation traffic jam. The motion of any single dislocation is increasingly hindered by the repulsive forces from all its neighbors. To overcome this resistance and continue deformation requires a higher and higher applied stress. That's strain hardening.
So it's basically dislocations getting in each other's way. Very cool. But you said it makes the material less ductile. Can we undo that if we need the ductility back?
Yes, we can. The effects of cold working, the high strength, low ductility, high dislocation density, stored strain energy, can be reversed or modified by heating the metal in a process called annealing.
Okay, let's talk about annealing then. What happens when you heat up a cold work metal?
Annealing involves heating the metal to a specific temperature, holding it there, and then cooling it. This allows changes to occur in the microstructure that counteract the effects of cold working. There are typically three stages: recovery, recrystallization, and grain growth.
Stage 1. Recovery. What does that entail?
Recovery happens at lower annealing temperatures. During recovery, some of the stored internal strain energy from the cold work is relieved. Atoms have more mobility at elevated temperatures, allowing dislocations to move slightly, annihilate some partners, and rearrange themselves into lower energy configurations, like forming networks that define low-angle boundaries or subgrains. The overall dislocation density decreases somewhat, and some properties, like electrical conductivity, start to recover towards their pre-cold worked values. But the main grain structure isn't significantly changed yet.
So recovery offers some relief, but doesn't fully reset things. What's next?
The next stage, usually requiring higher temperatures, is recrystallization. This is a much more drastic change. Here, completely new, strain-free grains start to nucleate and grow within the highly strained, cold-worked matrix. These new grains have very low dislocation densities and are typically small and equiaxed, roughly equal dimensions. They grow until they eventually consume all the old, deformed, high-energy grain structure.
So it's like wiping the slate clean and growing fresh grains.
Pretty much. The driving force is the large difference in internal energy between the heavily strained, cold-worked state and the strain-free, recrystallized state.
And what does this do to the mechanical properties?
Recrystallization effectively restores the mechanical properties back to their pre-cold worked levels. The material becomes softer, weaker, but much more ductile again. It reverses the effects of strain hardening. The process depends strongly on both time and temperature. Higher temperature or longer time leads to more complete recrystallization.
Is there a specific temperature where this happens?
We often define a recrystallization temperature technically, the temperature at which the process is complete in about 1 hour. It's usually somewhere between 1/3 and 1/2 of the metal's absolute melting point. But this temperature isn't fixed. Two big factors influence it. First, the amount of prior cold work. More cold work actually lowers the recrystallization temperature. There's more stored energy to drive it. Second, the purity of the metal. Impurities tend to hinder the grain boundary movement needed for new grains to grow, so impurities generally raise the recrystallization temperature.
And this relates to hot working versus cold working.
Exactly. If you deform a metal above its recrystallization temperature, that's hot working. Any strain hardening that occurs is immediately undone by recrystallization happening concurrently. So the material stays soft and ductile, allowing for massive shape changes. Deformation below the recrystallization temperature is cold working, where strain hardening accumulates because recrystallization doesn't occur.
Okay, so after recrystallization, we have new strain-free grains. What happens if we keep heating the metal or hold it at that high temperature? Is that the third stage?
Yes, that's grain growth. Once recrystallization is complete, if the material is kept at an elevated temperature, the new strain-free grains will start to grow larger. Smaller grains will tend to shrink and disappear, while larger grains consume them and grow even bigger. This can happen in any polycrystalline material at high enough temperatures, not just ones that were cold worked.
Why do they keep growing? What's the driving force now?
It's driven by the reduction of total energy associated with grain boundaries. Grain boundaries themselves have a certain surface energy. By reducing the total amount of boundary area, which happens as average grain size increases, the overall energy of the material is lowered. Microscopically, this happens by atoms diffusing across the grain boundary from the shrinking grain to the growing grain, causing the boundary to migrate.
And bigger grains generally mean lower strength, right? Back to the hole pitch idea.
Generally, yes. For most applications where strength and toughness are paramount, we prefer a fine, uniform grain size. So grain growth during annealing is often something engineers try to control or limit. If a material ends up with grains that are too coarse, you might need to plastically deform it again, cold work, and then do another controlled recrystallization heat treatment to refine the grain structure back to something desirable.
Wow. Okay, so we've gone from single atom movements and line defects all the way to controlling the final properties of bulk materials through deformation and heat treatment. It's quite a journey.
It really is. We've seen how these tiny imperfections, dislocations, are paradoxically responsible for both the ability of metals to deform plastically and the mechanisms by which we make them stronger. Understanding slip, twinning, how boundaries impede motion, how impurities pin dislocations, how density increases with work hardening, and how heat treatments like annealing can reset the structure, it all ties back to controlling dislocation behavior.
From making that aluminum can strong enough to hold pressure but ductile enough to form in the first place, to designing alloys for extreme environments, Using these principles, it really highlights how materials science is about manipulating structure at these incredibly small scales.
And that brings us to a final thought for you, our listeners. We've discussed the established ways to control dislocations and grains reducing size, alloying, work hardening, annealing. But looking forward, as we push for materials with even more extreme properties, lighter, stronger, tougher, more temperature resistant, what completely new strategies might emerge? How might future scientists manipulate dislocations or grain boundaries with even finer precision? Maybe using nanoscale techniques, or even controlling things atom by atom to unlock material properties we can barely imagine today.
A fascinating question to ponder. What's the next frontier in controlling these fundamental mechanisms? Thank you for joining us on this deep dive into dislocations and strengthening, based on Callister and Rethwish. We hope this made these complex but crucial concepts a bit clearer and sparked your curiosity about the microscopic world that dictates the behavior of the materials all around us.